Alright, so what's up guys? Alright, so we're revisiting this K380, my first video I ever made. By the way, really quick, thanks for everybody who left a message on that. I think it was mostly people who were just trying to figure out how to put the keycaps back on, but yeah, I'm glad I was a little help, and it was great to hear you guys figured your stuff out. Okay, so nobody ever reads the description, but as you can see, something happened. So basically, the long story short is the fix worked, and the keyboard worked for like a year and a half, but then after that, some other keys went out. And it was no fault of the original fix. I think this membrane is just really junky. So yeah, I think it's not a question of if, but when. So I think basically your keyboard is going to break. Anyway, if you don't get through this whole long video, just to sum it up, do not throw your keyboard away. Your broken keyboard is worth something. I could at least get you like $5 off eBay. That's at least a beer, and you save some e-waste from the landfill. So yeah, looking back over that fix, I realized it wasn't for everybody. It did require a bit of art and I think a little bit of luck. So I wanted to come up with another solution, and you guys have been asking for it anyway. Hey, do you think it's possible to put a mechanical switch on that PCB? Work on it. Mechanical switch! Alright, it was just one dude, but you guys know you're thinking it. And I know some of you guys are thinking, why bother?
Already dead.
And I was going to buy a new keyboard, but the thing is, okay, I trash on this K380 a lot, and the membrane does suck, and it is going to be like e-waste. But the one thing great about it, aside from being able to connect to 3 different devices, which was copied by everybody else, but the thing is, what's great about this is just the battery life. It just has insane battery life. The membrane sucks and all that, but when it comes down to it, it all comes down to this and this little PCB here. I can try and design my own Bluetooth keyboard from the ground up with like a ESP32 or something like that, but there's no way I'm getting close to the 2-year battery life that Logitech got. So yeah, kudos to the engineers they got over there. Okay, and I was shopping around for mechanical keyboards, and if I did have to buy one, I was kind of leaning towards these Keycrons. It's pretty good looking keyboard. But the thing is, yeah, I heard they got like terrible battery life, like maybe like a week or 2 weeks. And yeah, I just can't do that. I hate charging stuff all the time, so 2 years battery life is just insane. Another problem is, yeah, all of these keyboards they're kind of just followed suit for the pattern or the design. So they took the function key out from this bottom left, and I think that's okay for Windows users. But for Mac users, we need that function key. That's how it is for the standard Apple keyboard. And I don't know, I just want that function key on the bottom left. They moved it over here, but yeah, it's not working out for me. Okay, and another thing, they had to move to full-size keys for the arrow keys, so they don't have the half keys that the K380 had. And in order to do that, they basically had to shift the arrow keys over and cut the shift key in half, which, I don't know, to me just feels kind of lazy. And of course, I was looking at the Logitech mechanical MX keys, but it's basically the same story with the layout. The battery life is great, but yeah, I don't know why they got rid of that function key. All right, so we got this broken K380, but with a really nice PCB. And I know it looks like these manufactured products, it could be kind of intimidating. It looks like everything is custom, and for the most part it is. But when it comes to the components, they're pretty much standard. So what we have here is a 1mm pitch, 23-pin flex connector. So wouldn't it be great if we just designed our own mechanical keyboard PCB that we could plug this K380 PCB into? And this is it. I got the function key back, and don't worry if you're a Windows user, you could actually switch these in software. But I gave you the option to just solder some jumpers, so you could actually switch the function and control in hardware. And yeah, I think it came out great. It's nice and compact and clean. I call it, if I wanted to do the marketing wank, I could call it a zero footprint. And we got the full-size shift key back. All right, let's just do some quick calculations, because if you're looking for a quick, cheap fix, this isn't it. I didn't know anything about mechanical keyboards before I jumped into this, and yeah, those guys are freaks. Yeah, there's crazy like otaku and like nerds. They spend a lot on their keyboards. They could go like up to like $400, $600. I went for basic stuff, but let's just do the calculations here. So switches, I bought 2 sets. I got these Gateron low profiles, which are about like $20. And then I got these Kales, which were like about $30. So you got that, so $20-$30. The keycaps are about $20. And I went for the basic ones. They could go up to like $200. Again, these guys are freaks, but I went for basic $20, and I think these keycaps are great. but it'll be like 20 or $25. You need sockets. That's about like $7. You need stabilizers, which help push up like things for like the space bar because it's so they're like nice and balanced. You need those, and that's going to run you another like $7-10. All right, so far we're like at least $54, and that's not including the PCB and the case. So I'm being completely honest. If we go back to actually the original repair video, I think the number one comment was just buy a new keyboard. And yeah, people like to do that. And yeah, you should totally do that if you want. But if you want another option, let's go back to that MX Mechanical. All right, these things go on sale often, but I don't know what the price is going to be when you check. But this is what we got. And aside from getting that function key back, there's got to be like a value add. So, aside from storing the full-size shift key on the right side, I added knobs. And I'm selling the PCBs. So if you want to...
Shut up and take my money!
You could check down in the description. But I actually want to walk you through the design journey. All right, so let's differentiate more. And I'll mostly be comparing to the MX Mechanical because that's the closest to what we got here. Okay, so these are all the improvements we made. So first thing, sockets. So on the MX Mechanical, everything's soldered in. So if you wanted to replace the switches, you would actually have to desolder everything and put in new switches. So here they're hot swappable. So sockets, you got it. And then we come to the power, and for me personally, I prefer just like rechargeable nickel metal hydride batteries. And this thing's got 2 years battery life anyway. So I'm sticking with the AAAs, but you could actually stick AA's in here and that would last forever. But I'm also giving you the option to use lithium polymer. And when I was looking at the MX Mechanical, I was looking at some of the complaints that people had about it, and it looks like they actually reduced the battery life to about 10 months. So still not bad, but nowhere near the K380. But here you could just stick in as big of a battery as you want. And that also helps with the next thing. This thing is RGB ready. So I set it up so you can add neopixels, but if you want to use a single color LED and save energy, you can do that too. And another big complaint people had about the MX Mechanical is that the sleep on the backlight was a little too aggressive. But here you could set it up however you like. If you want to burn loads of energy, go for it. And well, look, I'm not recommending this, but I did engineer this thing to handle the top end ratings of the components you might want to use. So I didn't cheap out there. So if you were to use NeoPixels, you could technically push 5 amps through this thing.
Stop it. Get some help.
But don't do that, especially if you don't know what it means to push 5 amps through anything. And yeah, like I said, I added knobs. We'll talk more about that later as well. And there's some other stuff too, but we'll get into that. Okay, but in the end, why? Well, as you can guess from the channel, I like fixing things and refuse to accept that things just break and I should just keep buying new stuff to replace them. The manufacturers could easily solve this problem, but of course they don't want to. Logitech even talked about creating a mouse that would last forever, but that, okay, wait for it, required a subscription. So nice. So this is what we got here. Replacement switches, replaceable battery, and these PCBs like rarely ever fail. So this keyboard is something I can confidently say that I will use until the day I die. Or until I get bored of it, as the gods intended. All right, trying to figure out how to get my own key switches to connect to the K380 is probably the least interesting part of this video. If you watch my Apple repair video, I kind of explained briefly what a matrix was. I'll link that down below, but basically if you figure out the matrix, then you could find out what pins to connect to get a key press. So I did a quick search and I found this Reddit post where some other guy was messing around with his K380. And some poster said that he figured out the matrix and he posted this. So I thought, cool, I could save a lot of time. But for some reason, I don't know, he'll add the pins for the columns but not the rows. And these pins don't even go in order. I don't know why. So who does this? So it was like almost help, but it wasn't. I don't know. So anyway, I had to actually manually go and connect each pin to figure out what was what. So this is it right here. Okay, and once you have that, basically you just have to go through the trouble of routing everything. And honestly, that took a heck of a lot of time. So if you want to try this yourself, I just really recommend you start with like 0.25 millimeter traces because space is really cramped. Okay, and one thing I did was I created my own footprint for the switches. I wanted to make things universal, so I set things up so you can use sockets for the regular MX switches and for the Gateron low profiles. I wanted to add the Kale low profile sockets too, but they decided to use a strange arrangement, and that just made overlapping holes. So those Kales are out for being strange. So yeah, I wish these switch manufacturers would just agree on one conventional layout so we don't have to mess around with these proprietary formats. I'd say everyone should just use MX footprint since that's been around the longest. And I also made this hybrid setup for the LEDs, so you could use either NeoPixels or a single LED with a resistor. I'm not using LEDs. My main thing is battery life, and I never use the backlight anyway. But I know you RGB freaks are out there, so I added it. but it's easy enough to solder them on yourself. And there's some other design touches I added, but we'll get to that as we move through them. But I think the real interesting thing is how I got those knobs in, so let's get into that. So I added 2 encoders with center buttons, and I basically wanted to increment something when I go one way and decrement when I go the other. And I was originally just going to steal the media keys in the function row. Like I think I've never ever used any of these except the volume up, down, and mute. The play, forward, and reverse, I think I only ever just accidentally hit those. And these F4 to F7 media keys, I've never used. So I thought I'd use the volume buttons for one encoder and the play, forward, reverse for the other set.
But why?
Yeah, why have knobs that do what buttons already do? Because knobs are awesome, what else? But yeah, we're not going to be that lame. You would have been able to remap those keys to do whatever you wanted. But, well, when figuring out the matrix, I came across bonus buttons. It's these in yellow here. They're for the European and Japanese keyboards, and I think all K380s share the same PCB, and it's only the actual membrane that changes. So, well, that brings us to one thing. This design is only for the US keyboard. If you want one in any specific language, let me know down below, and maybe if enough people ask for it, maybe I can design one. But anyway, we're going to use these extra buttons as our encoder keys. And for all those non-English speakers who are mad that I'm using their special characters to trigger macros at fart noises,
I guess all I can say is sorry. I'm the bad guy.
Verloot me. Anyway, so how do we get these keys to do whatever we want? Well, on a Mac, we're using Carabiner, and on Windows, you can use Auto Hotkey. What are these? Well, basically, they allow us to remap the input received from keyboards or mice to whatever we want. I tested Auto Hotkey and it works, but don't use Windows too much at the moment. But as for Carabiner, it's awesome. And they're both open source and free. I don't even want to use Logitech software anymore. It just keeps getting more bloated. Even the software for my Razer mouse is buggy as hell. So Carabiner does everything for me. And yeah, it doesn't have a nice UI. I'll walk you through that later, but it's just as reliable, if not more, than the crap coming out of the big manufacturers. So right now I'm still just messing around, but I got the top knob for volume and the bottom knob. If you got a 4K monitor, you'll get this, but it's just to increase and decrease the size of the font. But you could even get it to be app specific. So you could use the same knob to change the audio levels for clips in DaVinci Resolve, change the brush size in Photoshop. And this is a fun one, quickly change the trace width in KiCad. Really, if there's a hotkey available for what you want to do in an app you're using, you can set these to whatever you want. But that's the software. Let's get back to the hardware. So what I want is this. When I turn the knob this way, it will trigger one button. And if I turn it the other way, it will trigger another. And the center button, you can map to something else. Won't go too in depth of how an encoder works. If you want to learn more, you can check this guy's video. But basically how these work is that there are 2 brushes slightly offset from one another. And as you turn, they will open and close a connection to a common ground. So they pulse on and off. And the important thing is that they follow one another. You don't need to know everything, but the important point is, let's say we pick one of the brushes, let's say A. These are pulled high, by the way, so that means high is off. Anyway, when A goes low or turns on, all we need to do is see where the other brush B is. If it's high, it's turning in one direction. If it's low, it's turning in the other direction. And that's how we know what direction we're turning in. Easy? Easy. To see how we can manipulate this in code, let's take a quick look at an example sketch. So here we're checking the state of A, again, looking for when it goes low or turns on. But importantly, we only want to register that trigger once, so we should only trigger if the previous state was high. This is called the falling edge. So if we're stuck in low, it doesn't just keep triggering. So this checks a state, we got the code here, then finally it writes that state to last state. So if A goes low, and only if it had previously been high, then we run this. A quick check of B tells us what direction we're turning in, and in this case, if it's high, we do this. And if it's low, we do this. And here we can just turn on a relay or a transistor, or in this case, we'll use a photocoupler. So that's it in a nutshell, and I've really been going on about battery life this whole time, and I want to keep all that glorious battery life of the K380. So a microcontroller is out, and they make ICs that do this, but I want to sell this thing, and they're way too expensive. And after seeing how much power they consume, they're also out. So what we're going to do is we're going to recreate all this code without any microcontroller. Are you ready? All right, now look, all you guys have ADD, and I have ADD. Everyone has the attention span of a hamster, so are you guys ready? All right, let's do it. All right, we're going to use a 555 timer to create a pulse that triggers our photocoupler to connect the leads of our button. We're using a 555 timer in monostable, or what's called single shot mode. I'd explain that here, but it'd take too long. And I'd link a good video that explains how a 555 timer works, but haven't found one that's succinct and doesn't treat you like a toddler. But I'll link a good website down below. Anyway, what this does is when we pull a switch low, turn it on, it turns an output for a set amount of time set by an RC circuit here. The timing can vary depending on what resistor and capacitor value you use. Here we're using a potentiometer so we could vary how long the button is triggered via the photocoupler. But the problem is the timer only starts after we release the button. So going low will turn on the output and it won't start the timer until after it goes high again. Now we got the detents on our encoder so it should always land in an off state, but we don't want this. We want to trigger exactly on the falling edge. So we're adding this capacitor setup on the trigger. Probably smarter people out there that could explain this better, but my analogy is that this capacitor is like a taut drum. So when the switch gets pulled low, this drum gets pulled in this direction, but it's a drum so it returns quickly. And don't get me started on conventional versus electron flow. Either it's pushing or pulling, however you want to think of it. And the diode here is like a gate valve, helping it move quickly in one direction. If you could explain better, do it down below. Anyway, it turns this switch going low into a pulse, and even if I hold it low, it will pulse like this, right on the falling edge. Even if I release it way after the pulse. That's all we care about. And if we change the timing with the pot, we can get it to trigger for shorter or longer, right on that falling edge. So that's the important part of the code. Catching the falling edge and triggering for a set amount of time. All right, we got that sorted. One quick housekeeping thing though, when we power the circuit on for the first time, it will trigger if the switch is held low. So no falling edge, it just started low. So not like you're going to be turning on and off your keyboard all the time and have the bad luck of having your encoder in the low position, but I don't want that. So we could add another RC circuit to this pin that will delay the 555 from being able to activate the output. So turning on, here you can see the RC curve delaying the activation of the 555 in blue, and the output in yellow is not activating. Okay, but what about this if statement? How do we do that? Well, we use a demultiplexer. Think of that as basically just a routing switch. And now we'll use the output of the B brush. So we got this output pulse triggered from the falling edge of A. We feed that into the demultiplexer. And depending on the state of B, which we feed into the input S here, it will either route the signal from A to this output or this output. So like the code, if B is high, send the signal this way and trigger this key press, and if B is low, trigger this key press. So let's see what that looks like. So here channel 3 in purple is the encoder state A, 4 in dark blue. On the bottom is the state of B. Channel 1 is one output coming out of the demultiplexer, and channel 2 is the other. So if we turn clockwise, we see here that yellow channel 1 triggered. And note again how the signals of A and B follow one another. And if we go counterclockwise, we see channel 2 triggered. So ain't that great? Let's try counterclockwise twice. Clockwise 2 times. Brilliant, huh? But a bit of a problem. What if a freak with anger problems turns the knob too fast? We get this. So the state of B is changing in the middle of that output pulse from the 555. So that high signal is getting routed to that other part of the if statement. We don't want that. So remember that pin we used to prevent triggering when powering on? Well, that's the reset pin. And if we pull that low, it resets the circuit. So how about we use the output of the 555 to turn on a MOSFET and pull that pin to low when an output is triggered. So it triggers and then just turns itself off. And here I'll just add an LED so we can see the output turn on and off. And you guys are in for a treat. I partnered with the science department at the University of Kobe here, and they gave me access to their electron microscope. Really grateful to them for that, by the way. So we can show you exactly what happens inside a 555 as it turns itself off. Abeli-san, take it away.
We have this model equipped with a window, so you can see just what happens to the light.
Oh, but wait, if it turns itself off, then it probably won't be on long enough to register a key press. Okay, so we can't do that. We could take the output of the 555 and use that to trigger another 555, but then we'd probably need one for each channel, and that'd be 3 555s for one encoder, and that'd get ridiculous. Wouldn't it be great if we could just take the value of B at the moment A goes low? Well, we can. So introducing the D flip-flop, one of the simplest forms of data storage. So this is used to store a bit on the rising or falling edge of a clock cycle. Think of our encoder as a clock. Here we're using a D flip-flop that works on the rising edge, so going from low to high. So when the output of our 555 timer goes high, it stores the value of B at that exact moment. And it presents the value to 1Q here, which we feed into our demultiplexer. And the value at 1Q will not change until the output of our 555 goes low and then high again. That is, we move our encoder another indent. Now, a couple of issues. Is our D flip-flop fast enough to store and present the value at B? Or will our demultiplexer route things so fast that an old value of 1Q can be used? Here we get into the propagation delay of the flip-flop and the turn-on time of the photocoupler. And luckily, our photocoupler isn't fast enough. Never was more happy that a component was too slow. Though 4.2 microseconds is nothing to turn your nose at. And so here's our final circuit. A complete recreation of our code. We got the 555 to read the encoder and trigger this if statement when it goes low. And here it automatically does the last state part check because it resets on going high and will only trigger on a falling edge. And here we use the output of the 555 timer and its assignable timing to do this digital write. And quick word about the output here. I originally thought about MOSFETs to connect the pins of the K380 matrix, but then my head started melting trying to figure out how to share the voltage differentials of the circuit with that of the K380. Then I remembered photocouplers. So if you don't know, they're basically just like solid-state relays. So I can have the circuit completely isolated from that of the K380. The if-else here is the demultiplexer, and we're using the D flip-flop to get that instantaneous read of B and to hold that value for the entirety of the output pulse, so it can be routed to only this if or this else. Anyway, that's a theory. Another order to DigiKey, and let's get this on a breadboard and see if it works. All right, all breadboarded up. So let's go right and left. And quick note, we were getting a residual blip on the old value of Q1 from our D flip-flop, and it seemed longer than 4 microseconds, but it seemed weaker than the full voltage, and it wasn't enough to activate the photocoupler. That's why we test these things. All right, so that was the routed output coming out of the demultiplexer. So here's the output coming out of the photocoupler. As you can see, that slight pulse from the residual value of Q1 isn't triggering the photocoupler. And that's it. Now we got no crosstalk, and we got nice clean activation pulses for the direction we're turning. And let's go really fast. Other direction. And really super fast. And we got them all. All right, let's hook this up to a K380 PCB and see if it works. So I got this hooked up to the volume up-down pin. So volume up and volume down. So yeah, nothing like having a crazy idea, working it out on paper, putting it together, and having it work. The feeling is like magic. Every time, I'll never get sick of it. Anyway, now is the time when I'm supposed to brag about how smart I am, how I was able to do a bit more research and bring down the quiescent cost of a TLC 555 of 250 microamps to 40 microamps using this Renaissance chip. That would bring us down to about 54 microamps per encoder, so roughly 108 microamps. But then I decided to do a quick search of those Renaissance chips just to see if there were any good reviews of them, and I found this Reddit page. Okay, so I've been out of the Atmel world ever since I became an ESP32 fanboy, and I knew those old Atmel chips were spotty when it came to sleep, but did not know about these new At-Tinies, so that makes me like 7 years late to the party. So I started digging in more, and man, that 10 microamps at that 32 kilohertz clock cycle isn't really usable for what we're doing, but the sleep is crazy improved. And at sleep, we're looking at a sub-microamp, like up to 2 microamps quiescent, and that's real-world usable sleep. And it's saying we can wake in about 6 clock cycles, plus it has these really cool new interrupt features. We'll get more into all that in the next video. And the big star of the show is this new library, Mega Tiny Core. We'll go way more into that too, but basically it's like Arduino for adults. This dude broke out things like running bitwise ops on the registers into the main code and speeding things way up. And he like really went above and beyond with his documentation. So like this guy and the people working on this code, they're truly awesome. And moving over to like an At-Tiny Series 2 would be less than half the cost of the components for the circuit we just made and take up like a tenth of the space. And finally, I was actually going to include like an unpopulated footprint for an ESP32 so you could add one yourself if you wanted to run the NeoPixels. And that was really hard trying to find the space. I was just going to break out the pins for the NeoPixels so you could add your own daughter board, but an At-Tiny would solve all that. And that's not to mention that we'll have a full Arduino on board, so like with the backlighting, you could manage sleep yourself, add proximity sensors, even create your own routines for the NeoPixels. And how about using modifier keys to change the output of the encoders on the fly, so you could center click on the encoder to make it do completely different things when you turn the knobs. Then of course we got I2C and SPI, so you could add a display, even a touchscreen. There are loads of things you could do. So, Arduino it is.